Hello and welcome to this video on ensemble methods. Now that we have a strong foundation on how decision trees work, it's time to learn about the overall algorithms that are available at our disposal with respect to ensemble techniques. Now this applies both for classification and regression. We'll walk through examples of either one of those and the idea will be quite clear. So ensemble methods are basically an aggregate of weak learners that eventually help creating a strong learner. Okay. Now ensemble can be of two types. They can either be bagging or it can be boosting. There's a third type which we won't cover in this course, but we'll definitely provide further reading materials to study there. Now bagging comes from the idea of bootstrap and aggregation. Now, one way to reduce the variance of an estimate is to average together multiple estimates. So, if I have only one model, it gives a prediction and it can either be too biased or it can have a high variance problem, right? But when I decouple those responsibilities across 5 models, let's say, 5 very simple weak learners, then there's a lesser chance that I'll have errors in my model. So bagging uses something called bootstrap sampling to obtain the data subsets for training the base learners, and then eventually it aggregates them via some technique, which we'll quickly learn now. Let's try and understand what is bootstrap sampling, that is working on data subset. Let's just assume our overall data looks like this. Let's just assume that we have a few rows of data and a few columns. It goes like this. And these are the column names. And it's all filled with data, right? Now what bootstrap sampling is it will randomly pick this subset of data for training one model. It may pick a totally different subset, like this one over here, for a different set of for building another model, and then so on and so forth. It builds models on different subsets of data. There will be different rows and different columns that each model will be looking at, and eventually if you fit that one particular model on the overall data set, it will end up not performing very well, but the aggregation of those weak learners will end up creating a strong model. So bagging stands for bootstrap and aggregation. Now we just learned what bootstrap is. It's basically randomly selecting different data subsets and then fitting a model on each one and then aggregating the model. So let's just focus on the aggregation. In terms of classification, a popular technique for aggregation that is used is simply voting. So for example, if I have 5 models, 3 of them say this data point belongs to class A and 2 of them say this data point belongs to class B, I will simply choose class A as my final prediction because it's the majority. And then if I look at regression, I can simply average them out and we are done, right? So that's as simple as that. Popularly, we always end up using decision trees most of the time for any sort of bagging technique or even boosting technique for that matter. So without further ado, let's jump onto some code. So here I have the relevant imports. I'm going to compare a decision tree classifier, a normal vanilla decision tree classifier, a k-nearest neighbors classifier, logistic regression, and then compare all of that with random forest classifier and a bunch of others that we have, like a vanilla bagging classifier. So let me get the imports out of the way. This will take a minute. Okay, now that our imports are out of the way. Let us start with the iris dataset. And what we are going to do is come up with two objects, one for the decision tree classifier and one for k nearest neighbors classifier. And then we will use the bagging classifier to build multiple models of the decision tree classifier in one instance, and then the k nearest neighbors classifier for the other. Now, this n estimators equals 10 means it will literally build 10 models on different data subsets. Max samples can be 0.8. That means 80% of the data can be used to build one model. Max features is also set to 0.8. That means 80% of the columns can be used to build one particular model, not more than that. So let's run this. And then I've got some code written over here to generate some comparative plots. Now I think there's a small error which we can rectify and then rerun again. And we have our plot now. So you can see the decision tree suffers sort of a high bias problem. It's not able to fit the decision boundary correctly. Whereas in KNN, it looks like sort of an overfitting case, but does a much better job at classifying compared to the decision tree. Here is the bagging one, the bagging using KNN, and then the bagging tree. That means bagging was done using decision trees. Now, if I plot the learning curve again for different train test splits, then I'll get this plot, which means here, if you can see, the x-axis has the training set size in percent and then the misclassification error on the y-axis. That means lower the better. So you can see that the gap is minimum between train and test sets, reasonably minimum, when there's about 20% of the data that is used for testing. A commonly used technique in the family of bagging ensemble algorithms is randomized trees, or simply known as random forests. Now, a forest consists of a number of trees. So a random forest is basically just a set of decision tree models that have been ensembled using the bagging technique as discussed before. So a random subset of features is selected for the randomizing the tree, and as a result, the bias of the forest increases slightly due to averaging of less correlated features, and its variance decreases, resulting in an overall better model. Now, there's also extreme random forests, which basically means the splitting thresholds are randomized. So instead of looking for the most discriminative thresholds, thresholds are drawn at random for each candidate feature, and the best of these randomly generated thresholds is picked as the splitting rule. So if you go back to decision trees, we always pick the splitting criteria based on the information, the maximum information gain that we can get from a particular feature. But instead of that, if we can use random splitting thresholds, then it is proven that it helps in reducing the variance of the model further. That means it helps us to control overfitting. So that's a short summary on bagging. Let us quickly build a random forest classifier. And then all I need to do here is, and again, scikit-learn APIs are very consistent, so I can use the n estimators here again, and then all I need to do is rf.fit on my training set. Oops. And then once that's done, I can take my predictions on my test set. And then finally build a classification report to review the model. I will just wrap this around print to prettify it. And there we have it. So seems like precision and recall are great for class 0, relatively not that good for class 1, and then further degrades precision in class 2. And these are the number of data points that support this decision. Overall accuracy is 78%, right? So that's how easy it is to get started with random forest. All you have to do now is tune the different hyperparameters that are there. So if I just hover over random forest classifier, it will load up all of the documentation associated with it. So the n estimators is the number of trees. The splitting criterion can either be Gini or entropy, which will basically use information gain. The max depth of each tree can be set to control overfitting to some extent. The min sample split is basically the minimum number of samples that have to be present on a particular node in order for a split to happen. Again, this is a pre-pruning strategy in decision trees themselves. So if I set that to 100, if there aren't more than 100 data points in a particular node, no split will happen, and that will result to controlling overfitting and ensuring each data point does not go sit in on its own node, achieving 100% training accuracy and doing abysmally bad in the testing set. The rest of them again are fairly self-explanatory. The max features is something called auto, which is interesting, which by default uses the square root of the total number of columns that you have in the data set. So if I have 16 columns on my data set, each decision tree will be built by 4 features randomly selected for each tree. I can also use different things here. I can provide a float like I did before in the bagging classifier, set it to 0.8 so that it uses 80% features, and so on. Max leaf nodes, again, these are the maximum number of leaf nodes that can be present in a particular decision tree. Min impurity decrease is basically, again, if I don't have a significant lift, do not split that node further. Bootstrap will obviously be equal to true, which again means that all of the dataset will be considered when choosing a subset for a particular model. So for example, let's say I selected a particular data point and used it to build model 1. That dataset can also be a candidate for selection if I choose to build model 2. If you set bootstrap equals false, then that particular data point, if selected for model 1, will not be selected for model 2. So those are some of the different hyperparameters that you can tune either using grid search or using random search or through manual trial and error or iterations. And that is a piece on bagging.